So just to again tell you that while you do all this, okay. So this is at some point I am stuck with this kind of an equation, right? So can you tell me what is the BFS? Exactly, the one which is listed here. This is my B, or 4 and 6 are my B, 1, 2, 3, 5 are my non-basic, right? At this point, my objective value is 2. Now, when I look at the objective function, this is clearly not locally optimal because the coefficient of x2 is positive, right? So, but then that means x2 is the only possibility for me to be the leaving variable. But now, yes, here it is great, I can increase x2 to be equal to 1, but x4 cannot be increased. So if you actually look at this solution, this solution is right? And then clearly this x6, x4, this is a diagonal matrix 1 and 0, this is invertible, but even the column corresponding to x2, x6 and the column corresponding to x2, this is also full rank. This is like I think 1, 0, minus 2, minus 2 or plus 2, plus 2. This is also full rank, right? And not just that, I think x5 cannot come, but probably, yeah, even x3 and x6 are also basic feasible. So the same vertex here, the same solution here, you can have 4, 6, you can have 2, 6, all those are invertible, right? And all those invertible, I know that everything else is 0. So it is a basic feasible solution, right? So it's a serious concern. What if we keep circulating between these 3 basic feasible solutions? So it turns out that actually the implementation is not very difficult. There is a simple solution which takes care of it. And so I have given you an example where it can potentially get stuck if you're not smart enough, if you just take a random choice of the leaving variables. But what you know is something called Blind's rule. It is artificial. I'm just going to tell you the Blind's rule. The proof is there in the notes. It's technical and it doesn't give us any extra advantage. You will just forget about it after this. You'll never encounter it. So I don't want to go into the proof. But if you are interested, you can see the proof. It's like 2 paragraphs. It's just, so I will tell you the idea of the proof also. But yeah, what Blind's rule does is, so okay, one thing could be, you might say, oh, whatever has the highest coefficient, right? In some sense, that's the highest increased direction. You might want to pick that. It turns out it doesn't work. Okay, so what they say is, you first decide on an ordering, your favorite ordering, whichever one you want, right? Let's say this is the favorite ordering. This is the 1, 2, 3, n. Then whichever, look at all the coefficients which are positive for the non-basic variables. Look at the first variable from that list, which has a positive coefficient. Pick that. The amount of coefficient, the value of the coefficient does not matter. It's basically saying smallest variable here, like, okay, smallest is a bad word, but smallest index variable whose coefficient is positive. I'm going to pick that. Okay? Why it works? Proof is there in the notes. But this is the, okay, so if you fix that strategy, always, it's not a random choice of how you are deciding the leaving variable. So, what's the rule? Pick the first positive coefficient from this order leaving variable. Okay? This is called Brand's rule, and if you do that, you have a guarantee that you will not get stuck into any cycle. Okay? You might be wondering why. So, what is happening? So, basically, the way things work is that if now you have picked x2 here, next time you will only see variables as a positive coefficient which are after that. So if you have picked x2, you will not circle back in some sense. So if you look at the proof of this, so it will start by saying, oh, let's say xt is the highest leaving variable in your cycle. Okay, but how does it matter? Xt is the highest index leaving variable, that means it's the highest index entering variable also. Right? This is a cycle. That means all variables, if they leave, they will enter once again. So you have a cycle of B1, B2, B3, B6 or whatever, and one variable leaves here, at some point it has to enter. It will just analyze, okay, this is where leaves, this is where it enters, let's say. S is the leaving variable at B whatever, I don't know what I have written here, but this is where T enters again. So, you look at the two standard form equations here and here, and you will basically argue that, you know, the coefficient of excess had to be positive here. Why didn't you pick excess? Why did you pick xt? That's the kind of like analyzing all the coefficients. Oh, it was going in the right direction, this is positive, but you know, you have this multiple dependencies that for the leaving variable this coefficient has to be positive, this variable has to be, so with all that you can do that. Okay, but again, it does not give a lot of things for future, but it's a possibility. How do we avoid it? Using this ordering. Sounds good? Okay. So this finishes the idea of simplex algorithm. So let me just write this implementation. Actually, you can help me out. The first is put everything in standard form. Okay? I think I called auxiliary here, so let me use auxiliary variables to find the first BFS. Okay? if you don't want to be very, very efficient or something, you can just introduce auxiliary variables in all the equations. Who cares? Right? And then just write minus x1, minus x2, minus y1, minus y2 up to minus y. Completely fine. It doesn't matter. So you use auxiliary variables for, let's say, each equation, change your objective function, solve the different LP to find the first BFS. You are convinced that this works, right? Then move from increasing objective volume. If at any point my BFS is locally optimal, stop. Right? And you know how to check that. This is basically looking at the objective functions. What are the coefficients? Any point, how to move from BFS to BFS, you know. Pick the positive constant, probably with the ordering, with Blend's rule in mind. That's my leaving variable. Decide the leaving variable, look at the equations, see which variable is going to 0 first. That's going to be your leaving variable. So, sorry, you have entering variable and leaving variable. So, find an entering variable, depending on the entering variable, you decide a leaving variable. Okay, you get to the new BFS. You might go from a BFS to BFS where your vertex is not changing, but it will never be a cycle by Blend's rule. Since you keep increasing your value in finite number of steps, this will finish. But what we know is that for all the implementation, there are programs, there are linear programs which can circulate over exponential number of vertices. So this is not known to be polynomial time. Can anyone tell me why did I put quotes on known? Because there is no one simplex algorithm. Right? When we say this, it means from this class of algorithms which utilizes this convexity properties, is there an implementation like something like Blend's rule? Can I have one rule there depending on how I choose the leaving variable, how I choose the entering variable? Probably. That's how you become, suddenly from exponential to polynomial time. We don't know, whatever people have suggested have been shot down. That's the status. But thankfully, we have two. Okay, ellipsoid and interior point method. And ellipsoid method is polynomial time but not very feasible because of numerical accuracies and things like that. The idea there is that it turns out, not just for linear programs, for any convex program, you can solve them if you can solve the membership problem, which is saying whether a point is inside my feasible region or not. So if you are given oracle for that, you use it many times and then you can find an optimal solution. But that's the idea behind ellipsoid method. But that membership question is something that is going to be important for us from the next class itself. Okay, how do we find out whether a point is inside a convex area or not? Or how do we prove that a point is not inside a convex region? Okay, this question ship C is some convex body. How do I prove it is not element of C? Right? That is going to be the discussion from the next class. What people use is interior point method, and I don't know if you are in a patriotic mood, you can be proud because this was one of the main person who came up with this was Karmarkar, like an Indian dude. He is now in Pune, I think, but he was the inventor of one of those interior point methods, which is used heavily, which made him very, very rich. Right? So you are at the right class.